Hi learners and viewers, today we shall learn transpose of a matrix and its properties, symmetric and skew symmetric matrices, elementary row and column transformations, invertible matrices. Transpose of a matrix is obtained by interchanging its rows and columns. It is usually denoted by a dash or a transpose. That is, if capital A is equal to matrix Aij of order m by n, then it's a transpose. A dash or a transpose is equal to Aj with order n by m. Consider the matrix capital A is equal to, say, 2 by 3 matrix 2, negative 3, 5, 7, 8, 11. It's of order 2 by 3. Then its the first row is 2, negative 3, 5. And we shall make a new matrix by its first column as 2, negative 3, 5. Similarly, the second row is 7, 8, 11, and here it will be second column. So that is 7, 8, 11. And this newly obtained matrix is what is called a dash or a transpose, which order will be 3 by 2. Here what is the cell address of 5? That is in first row and the third column. So 1/3 position. And the same element 5 that appears in A transpose, in which position you see, that is in third row and first column. So what happened actually? That is the 1/3 position changed to 3/1 position. That is why we do say if A is equal to Aij of order m by n, then A dash will be Aji n by m. So what happens? Ijth positioned element in capital A becomes jith positioned element in A dash. Now properties of transpose of a matrix. Properties of transpose of a matrix. The first property, that is A dash dash, A transpose of A transpose will be A only. Why it is so? Let us consider capital A is equal to, say, Aij of order m by n. Then what is A dash? We know that this ijth position will be in jith position, therefore it will be Aji, and then this order m by n becomes a reverse order, that is n by m. Now if we consider this as our matrix and go for its transpose, that is A transpose, then this jith position element will be in ijth position, therefore we shall have Aij. And what will happen to this order? It will be in reverse order, that is m by n. Now Aij m by n, what is it? It is our A only, hence the proof. You can see if capital A is equal to, say, 2 by 3 matrix 1, 2, 3, P, Q, R, then what is A dash? A dash will be 1, 2, 3 column wise, P, Q, R column wise. Then we shall go for A dash dash, that is transpose of this matrix. That will be this 1, 2, 3 column becomes our 1, 2, 3, because we are interchanging columns into rows and rows into columns, and this PQR column becomes a PQR row. And what is this? This is nothing but a capital A. That is why A dash dash is equal to A. Transpose of a matrix is matrix itself. Now the next property is that Ka transpose is Ka transpose. Now let us see why it is so. Let a capital A is equal to Aij of order m by n. Then what is Ka? We know that is nothing but we have to multiply every element Aij by K. So that is K Aij. Order will be same M by N. Now we shall go for it's a transpose. So it's a transpose means what will happen? So Kij, this cell address Ij will be jth position. So that is Kaji of order N by M. And you know that we can take this K outside if you want. That is K into Aji of order N by M. Now what is this? This is nothing but in comparison with this one, we can see this is A dash. So that is equal to Ka dash. You can have a small homework, that is if capital A is equal to negative 1, 5, 7, 4, 1 by 2, 10, then verify that, 5A dash transpose is equal to 5 into A transpose. What you have to do is, so very simple. First of all, you have to find 5A, then you have to find its a transpose. Then again you have to find A dash, A transpose. Then you take 5, that is scalar multiple of A dash by 5, that is 5A dash. Now what will happen? You can see that both the answers, that is 5A whole dash and 5 times A dash, that will be same. That's all. Another property of transpose is that A plus B whole dash, transpose of A plus B, that is transpose of a sum will be sum of the transposes A dash plus B dash. This proof is again very simple. If capital A is equal to say Aij of order M by N and capital B is equal to Bij of the same order, then only we can find A plus B. Then what is A plus B? A plus B will be, we know how to add matrices. We have to add the corresponding entries. So that is Aij plus Bij. Order will be M by N. Then you have to find A plus B whole dash. Then what will happen? You know that the cell address will be changing. That is Aj and then Bji, and order will be N by M. So you can see that is equal to Aj of order N by M plus Bji of order N by M. And then what is Aj N by M in comparison with Aij M by N? That is nothing but A dash. And in the same fashion, you can see in comparison with the Bij of order M by N, what is this Bji N by M? That is nothing but B dash. Hence the proof. Again, a small homework for you. That is very simple. If capital A is equal to say matrix 1, negative 2, 5, 7, and capital B is equal to 0, 5, 8, 11, then verify that, A plus B whole transpose, that is equal to A transpose plus B transpose. That's the property just we learned. Transpose of a sum becomes sum of transposes. So what to do here? So very simple. First of all, you have to find A plus B. Then you have to find its a transpose, that is A plus B dash. Call it as equation star. Then you go for A dash, that's your third step. Then fourth step, that is you go for B transpose. Then fifth step, you go for A dash plus B dash. Call it as double star. You can verify that this result and this result is same. That's all. Last property of a transpose is like this. That's simple. AB product, then transpose, that is B transpose, A transpose. So to recollect this one, foreigners are saying this is nothing but a dressing undressing principle. Dressing undressing principle. What do you mean by that? That is, suppose we are wearing socks first of all and then shoes. That is the wearing order. Socks first, then shoes second. Then to remove, what's the order? We have to remove shoes first of all and then socks. That is why foreigners are calling this as dressing and dressing principle. We wear socks, then shoes, we remove shoes and then socks. That is why A, B, that's a wearing order. The removing order means B dash and A dash. A homework for you. If capital A is equal to 0754 and capital B is equal to negative 15811, then verify that. A B whole transpose is equal to B transpose A transpose. So I will give you the hint or the procedure. That is, first of all you have to find A dash and B dash, and second you have to find product AB. Third step, you go for transpose of the product and call it as a star. Then fourth step, you go for B dash A dash multiplication and call it as a double star. You can verify that this and this result are same, hence the verification. Symmetric matrix. Symmetric matrix. Now consider a square matrix. Consider a square matrix. Capital A is equal to, so let us consider a 3 by 3 square matrix. 3 by 3 square matrix. 1, 2, 3, 2, 4, 5 and 3, 5, 7. Now we shall find it's a transpose, that is A dash. So what will happen? This row becomes our first column and second row becomes our second column and third row becomes our third column. 3, 5, 7. So you can see order is same, and the corresponding elements also same. That is 1 is 1 and 2 is 2 and 3 is 3, like that 7 is 7. So you can see that here A is equal to A transpose. When such things happens with a square matrix, it is called a symmetric matrix. So a square matrix, capital A is called a square matrix. Capital A is called symmetric, a symmetric matrix if A dash is equal to A. That is, if capital A is equal to Aij, a square matrix of order m by m. Why m by m? Because it is a square matrix. It is a square matrix. Then A dash, what is A dash? That is equal to Aj of order m, means m by m. Then if A dash is equal to A, that means if Aij is equal to Aj, that is if Aij equals Aj for all Ij, then we can say capital A is a symmetric matrix, square matrix. Capital A is a symmetric matrix. Now skew symmetric matrix. Skew symmetric matrix. Let us consider a square matrix. Let us consider a square matrix. Capital A, say of order 3 by 3. That is 0, 5, negative 2, negative 5, 0, 7, 2, negative 7, 0. Now, if we go for, it's a transpose. That is, our first row becomes first column here. That is 0, 5, negative 2. Second row becomes second column, that is negative 5, 0, 7. And third row becomes 2, negative 7, 0 here. Now, it is not equal to A, no doubt. But if we take a negative one outside from each and every element, then what will happen? We are having 0, then negative 5 becomes 5, 2 becomes negative 2 because we have taken negative one outside, then 5 becomes negative 5, 0 becomes unaltered, and negative 7 means here 7, negative 2 means here 2, 7 becomes negative 7, and 0 unaltered. And you can see negative 1 into A. So, here what is the property? That is A dash is not A but negative A. If it happens, then the square matrix capital A is called skew symmetric matrix. Skew symmetric matrix. Let capital A is equal to Aij, a square matrix of order m. Whenever we write m alone, its meaning is m by m means square matrix. Means a square matrix. Now, capital A is called a skew symmetric matrix. A skew symmetric matrix. A skew symmetric matrix. If A dash is equal to negative A. What do you mean by that? A dash means Aj of order m. Now the requirement is A dash is equal to negative A. That is A dash. What is A dash? Aj of order m is equal to negative of A. So A is Aij of order m. So you know that this negative stands here, that is scalar multiple by negative 1. So we can take it inside, that is minus Aij order m. And now two matrices are equal. Therefore their corresponding entries are equal. Corresponding elements equal. So using that we can write Aj is equal to minus Aij for all ij. Then we can say that A is a skew symmetric matrix. So simply speaking, a square matrix capital A is equal to Aij is called a skew symmetric matrix if Aj is equal to negative Aij for all ij. Now we shall learn a theorem. For any square matrix with a real number entries, A plus A dash is a symmetric matrix and A minus A dash is a skew symmetric matrix. How to prove it? Let us prove the part 1. That is A plus A dash is a symmetric matrix. So take capital P is equal to A plus A dash. Now we shall show that P is a symmetric. We shall show that P is a symmetric matrix. And you know that capital P is a symmetric matrix if P dash is equal to P only. So let us consider P dash. So what is P dash? P dash is A plus A dash the whole dash. And we have learned a property of transpose is that is A plus B whole transpose, that is equal to A transpose plus B transpose. So using this theorem, here we can write that is A transpose plus A transpose transpose. And what is it? That is A transpose plus what is A transpose transpose? A transpose transpose is nothing but A. Now you know that addition of matrices follows commutative law. Therefore, A dash plus A could be written as A plus A dash using the commutative law. And what is it? That is P only. So we could prove that P dash is equal to P. Therefore, what is P? P means A plus A dash. Now P, when P dash is equal to P, P is a symmetric matrix. So A plus A dash is a symmetric matrix. Now we shall prove the second part. That is, we shall show that A minus A transpose is a skew symmetric matrix. is a skew symmetric matrix. Now for that we shall take a Q is equal to A minus A transpose. Now in order to show that Q is Q symmetric matrix, we have to prove that Q dash is equal to negative Q. So let us consider Q dash. What is Q dash here? That is A minus A transpose transpose. That is equal to A transpose minus A transpose transpose. That is equal to A transpose minus. What is A transpose transpose? That is equal to A only. Therefore, we can write A here. So that is negative of A minus A transpose. That is equal to minus Q. So we could prove that Q dash is equal to negative Q, showing that Q is a skew symmetric matrix. Skew symmetric matrix. And what is Q? Q is nothing but A minus A dash. That is A minus A dash is a skew symmetric matrix. That's all. We shall learn another theorem. That is every square matrix can be expressed as the sum of a symmetric matrix and a skew symmetric matrix. So what is the proof of this theorem? That is again very simple. Let capital A be the given square matrix. Capital A be the given square matrix. Now if we consider capital P is equal to say half of A plus A transpose. Given capital A square matrix, we can find A dash here. So we can define capital P is equal to half A plus A transpose. And we shall take capital Q, another matrix, as half of A minus A transpose. And we shall show that P is a symmetric matrix here and Q as a skew symmetric matrix. We have P is equal to half A plus A transpose. We shall show that P is a symmetric matrix. That is, we have to show that P dash is equal to P only. So let us consider P dash. That is half of A plus A transpose, the whole transpose. And we learned a property Ka whole dash, that is equal to K into A dash. Therefore, we can take a half outside, then A plus A dash dash. That is equal to half A dash plus A dash dash. So that is equal to half A dash plus A. So that is equal to half A plus A dash using commutative law. That is equal to P. So we could prove that P dash is equal to P. When P dash is equal to P, P is a symmetric matrix. And what is our P? P is our half A plus A dash. And now we shall show that Q is equal to half A minus A transpose is a skew symmetric matrix. In order to show that Q is a skew symmetric matrix, what we have to prove is we have to show that Q dash is equal to negative Q. So let us consider Q dash here. That is half A minus A dash, the whole dash, and we can take the scalar outside. That is half A minus A dash, the whole dash. That is equal to half into A dash minus A dash dash. So that is equal to half A dash minus A. Taking a negative sign outside, that is minus half A minus A dash. That is equal to minus Q. So what happens? When Q dash is equal to minus Q, we can say that Q is a skew symmetric matrix. Therefore, this matrix will be skew symmetric matrix. Thus, we could prove that capital P, the matrix half A plus A dash, which is nothing but a symmetric matrix, and capital Q half A minus A dash, which is nothing but a skew symmetric matrix. Now, what will happen when we add this P plus Q? You know that half is taken common, then inside the bracket a plus a dash plus a minus a dash, then of course a dash negative a dash will be getting cancelled, that is equal to a only. So you can see that every square matrix capital A could be written as a p plus q, where p is a symmetric matrix and q as a skew symmetric matrix. Hence the proof. Hence the proof. Hence the proof. That's all. Dear learners, now you can have one thought-provoking question. We have just learned that every square matrix capital A could be written as P plus Q, where P is equal to half A plus A dash, which is a symmetric matrix, and capital Q is equal to half A minus A dash is a skew symmetric matrix. Suppose another student is writing, say, capital A is equal to R plus S, where R is a symmetric matrix and S is a skew symmetric matrix. Then do you think that P will be same as R and Q will be same as S? Simply speaking, can you conclude that this expression A is equal to P plus Q is a unique one? That is, everyone will get the same P and Q every time. Please think over it and try to solve. One more homework for you, which is very simple. That is, express the square matrix capital A is equal to, say, 1, 2, 3, 4 as the sum of a symmetric matrix and a skew symmetric matrix Here the answer is very simple. I will give you the hint for that. That is, you take capital P is equal to A plus A dash and half of it. That is, you have to work A plus A dash first of all, then take half of it, then call it as a star. Then you have to show that P dash is equal to P, just to show that P is a symmetric matrix. Then again, you have to take another matrix, that is half A minus A dash. So you have to simplify A minus A dash first of all, then take half of it, and you can show that here Q dash is equal to minus Q. So P dash is equal to P means P is a symmetric matrix, and Q dash is equal to minus Q means Q is a skew symmetric matrix. And you can express capital A is equal to your P plus Q. That's the result, where P will be symmetric and Q will be skew symmetric. That's all. Elementary operations or transformation. There are 6 elementary operation or transformation, 3 of which are due to rows and 3 are due to columns. Elementary row or column transformations. The first one is the interchange of any 2 rows or correspondingly any 2 columns. We can represent it as, suppose we are interchanging ith row and jth row, we can write it as Ri double arrow Rj, or if we interchange ith column with the jth column, then we can write like this. So what is it? Suppose we have capital A is equal to, say, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we operate R1 interchange with the R2 elementary operation, that is, we are just interchanging the first and the second row. What should be the answer after the operation? That is, first row will be in second row and the second row will be in first row position. So we shall have 4, 5, 6 as the first row, and the present first row, that is 1, 2, 3 will be in the second position. So that is 1, 2, 3 here as the second row, and nothing change with the third row, so we have to write 7, 8, 9 there. That's all. This is the first operation, that is the interchange of any two rows or columns. The second elementary row or column transformation is like this. We can multiply the elements of any row or column in a matrix by a non-zero number. For example, suppose we are multiplying the ith row by a non-zero scalar k. Symbolically, we can write Ri transformed as k times Ri. We shall make it clear, that is capital A is equal to, say, 1, 2, 3, negative 5, 7, 6, 8, 9, 11. And if we choose a non-zero scalar k is equal to, say, 3, and we are operating, say, R2, second row transformed as 3 times R2, then after the transformation, the transformed matrix will be, you can say, that is 1, 2, 3. No change with respect to the first row and nothing change with the last row. Only the change is with the second row. Second row elements will be multiplied by 3, the scalar. So 3 into negative 5 and 3 into 7 and 3 into 6. That's all. So this is the transformed matrix. In the same fashion, we shall do with the columns also. For example, Ci transformed as a non-zero scalar k times Ci. We can make it clear, that is, if capital A is equal to the matrix 1, 2, 3, 4, and suppose we are transforming with the second column, that is C2 transformed as 4 times C2, then after transformation we shall have first column no change and second column that will be multiplied by the scalar non-zero scalar k, so that is 4 times 2 and 4 times 4, that is we shall have 1, 8, 3, 16. That's all after transformation. Now another elementary row or column transformation is like this. The addition to the elements of a row or column, the corresponding elements of any other row or column multiplied by a non-zero number. For example, suppose we are transforming the ith row, that is Ri transformed as, we can multiply jth row elements by a non-zero scalar k and then add those elements to the corresponding elements of the ith row. That is Ri transformed as Ri plus k time Rj. Or equivalently, we can go for ith column transformed as ith column plus a non-zero scalar times jth column elements. That is Ri transformed as Ri plus krj or Ci transformed as Ci plus kcj. Ri transformed as Ri plus krj means we are adding k times jth row elements to ith row, and Ci transformed as Ci plus kcj means we are adding k times elements of the jth column to the corresponding elements of the ith column. That's all. To make it clear, if capital A is equal to the 3 by 3 square matrix, say 3, negative 2, 5, 1, 4, 7, 5, 1, 8. And if you operate, that is second row transformed as R2 plus 3 times R3. Then what's the meaning of it? That is, we have to take the third row elements and multiply them by 3 and add to the second row. That's all. So after the operation, what will happen? Let us see. We can see that the change is with the second row only. Therefore, first row we can write as it is, there is no change, and the third row also we can write as it is, no change. Only the change is with the second row. So what will be that change? That is, we have to take the third row elements, multiply them by 3 and then add to the second row. That is 1 plus 3 times 5, 4 plus 3 times 1, and 7 plus 3 times 8. that is equal to, you can see 3 negative 2 5, then 1 plus 3 into 5, so that is 16, and here it is 7, and here it is 31, then 5 1 8. That's all. This is after the transformation. A simple homework for you, that is, if capital A is equal to the 3 by 3 matrix, say minus 1 5 half, then 7 8 11 negative 2 0 4, then operate R3 interchange with R1, the first operation. Second operation, that is R2 transformed as 7 times R2, and third operation is that R3 transformed as R3 plus 8 times R1, and the fourth operation is that R3 transformed as R3 minus R2 plus 4 times R1. So you have to do 4 answers separately. Don't do it successively. That is, first of all you will apply it and then apply it, not like that. This is one answer, and again take this A and do this one, that's the second answer, and again take this matrix, then do this one, and then do this one. That's all. Next topic is invertible matrix. Invertible or inversible matrices. Inversible or invertible matrices. If capital A is a square matrix of order M, and if there exists a square matrix capital B of the same order, such that AB is equal to BA is equal to the identity matrix, then B is called the inverse of capital A, and B is equal to A inverse symbolically. Also, A is the inverse of B. That is, for a given square matrix capital A, if there exists another square matrix of the same order, so capital B, such that AB is equal to I is equal to BA, then we can say that B is the inverse of A and vice versa. That is, A inverse is B and B inverse is A. In such a case, we can say that A is invertible. A is invertible or inversible. That is, once again, given a square matrix capital A. So remember that inverse can be had only with the square matrix, and it is not necessary that every square matrix shall have inverse. Let us consider one example. Consider the square matrix capital A is equal to 2 3 1 2, and another square matrix capital B is equal to 2 negative 3 negative 1 2. Now what will happen when we consider the product AB, that is equal to 2 3 1 2, then 2 negative 3 negative 1 2. We know matrix multiplication is a row column method. You can multiply to get 1 0 0 1. Also, when we consider the product BA is equal to 2 negative 3 negative 1 2 multiplied by 1 2 3 1 2, then also you can have 1 0 0 1. Therefore, AB is equal to I is equal to BA, showing that B is the inverse of A and A is the inverse of B. That's all. As I told you, only square matrix can have inverses. It doesn't mean that every square matrix shall have inverse also. So you can see that if capital A is equal to say 2, 3, 4, 6, then this is square matrix of course, but we cannot find a matrix we cannot find a matrix capital B, we cannot find a matrix capital B here in such a way that this matrix A multiplied by this matrix B is equal to identity matrix. B cannot find it. Therefore, here A is not inversible. Here A is not inversible. So remember that every matrix cannot have inverse. A rectangular matrix cannot have inverse. Inverse can be had only with the square matrix, and it doesn't mean that every square matrix shall have inverse also. One more question for your homework. Consider the square matrix capital A is equal to 1, 2, 3, 4, and I do say that A is invertible. A is invertible. That means you can find a matrix B such that AB is equal to I is equal to BA. Question is, how will you find that B here? I will give you a clue. Take B is equal to in general form, that is say A, B, C, D, and apply the equation A, B is equal to I is equal to BA. Then try to find A, B, C, D values. Then that way you can find B. Please try it. Thanks for watching Bentech.